Okay, let's go over a few example problems. In this example problem, a 50 kilogram iron block and a 20 kilogram copper block, both initially at 80 C, are dropped into a large lake at 15 C. Thermal equilibrium is established after a while as a result of heat transfer between the blocks and the lake water. Determine the total entropy change for this process. So, as far as assumptions are concerned, at this point, I'm going to go ahead and assume that the rocks are solid. Okay, so it's asking for the total entropy change. So the total entropy change would be the sum total of the entropy change of the copper rock or block plus the iron block plus the entropy change of the lake. So what I'm going to do is find the entropy change of each individual portion of the system. So again, this would be the entropy change S2 minus S1, and this is for a solid. I'm going to go ahead and also assume constant specific heats, so that the specific heat is not a function of temperature. So in that case, according to our equation from earlier, if you recall that the entropy change for an incompressible substance at constant specific heats would be the specific heat times the natural log of the final temperature over the initial temperature. That's for a solid. So we have the copper block and the iron block. Now, the entropy change for the lake would equal the amount of entropy that was transferred to the lake from the blocks, right? So we have entropy. We have the fact that the lake is a thermal sink, right? It absorbs heat with no perceived change in temperature of the lake. And so what's happening is that the blocks are giving up heat to the lake, causing the lake to have an entropy transfer to it by heat. Now, according to this problem, we're given that the blocks start at 80 C and they go down to 15 C. So we have the initial and the final temperature of each of the blocks. So if I wanted to actually get the total entropy change, I would have to include mass into this equation as well. So I have for the copper block, the mass is 20 kilograms. The specific heat is given in the problem statement as 0.386 kilojoules per kilogram Kelvin times the natural log of the ratio of the final temperature in Kelvin divided by the initial temperature in Kelvin. And that gives you the fact that the entropy change is negative, not the entropy generation is negative. The entropy change is negative due to the fact that there's entropy leaving. There's entropy leaving the block in the form of heat, entropy transfer away, and the entropy transfer away is causing this entropy change. Same thing for the copper block. The copper block has a mass of 50 kilograms. It has a specific heat of 0.45 kilojoules per kilogram Kelvin multiplied by the ratio of the final temperature in Kelvin divided by the initial temperature in Kelvin. That gives me an entropy change of negative 4.58 kilojoules per kilogram. Now remember that the entropy change, this quantity, it can be negative. The entropy generation has to be positive or zero. It's only zero when the process is reversible. So the way that the entropy change can be zero or can be negative is if the entropy transfer term is greater than the entropy generation term, right, where the entropy transfer term is negative, or if it's reversible, the only way for the change in entropy to be negative is if there's entropy transfer away from the system in the form of heat leaving the system, right? So this can be negative or positive. So if I go back to this problem, the reason why that the change in entropy of the blocks are negative is because there's heat being transferred away. And that total heat transfer is going into the lake, causing a positive increase in entropy change of the lake due to heat transfer to the lake. Now, the thing is, I don't have this Q. I don't actually know, and I don't have that quantified yet. So I have to go to a first law analysis. I have to go to a first law analysis in order to quantify the heat transfer to the lake from the two blocks. Now that can be done pretty quickly. So if I do a first law analysis, again, I'm not going to go through by starting by E and minus E out equals delta E system, but I can tell you that if I take the two blocks as the system, I have Q leaving the blocks to the lake due to an internal energy change for the copper block plus the internal energy of the iron block. This is equal to the total internal energy change is equal to the internal energy change of the copper block plus that of the iron block. Now it's constant specific heats, so my internal energy change would be approximated as MC delta T. So I have MC delta T of the copper block plus MC delta T of the iron block. All the parameters in this equation are known, so I can plug in all the parameters, and I get that the heat transfer to the lake from the two blocks is 1,964 kilojoules. Okay. I can go back and plug it in to the fact that I have the heat gain to the lake is 1,964 kilojoules. The temperature of the lake is 288 Kelvin. So that tells me that the lake has a entropy change of 6.82 kilojoules per Kelvin. So if I had this term, and this term together, I get that the total entropy change for this whole process is 0.67 kilojoules per Kelvin. And what's interesting is that that would be the entropy generated, because if you go ahead and if you go ahead and draw another boundary around the whole system, you can assume this to be an isolated system, right? So the delta S total has to equal the sum of the total heat transfer to or from the system plus the S gen. And if I go ahead and draw a boundary around the whole system, all the heat transfer is happening internally, right? I went ahead and I did a first law analysis or second law analysis by saying that the total entropy change is equal to the entropy change of the lake, the entropy change plus the entropy change of the iron block, plus the entropy change of the copper block. But if I go ahead and just include all these three components as one whole system, that whole system itself has no heat transfer coming out of the system, right? It's all happening inside. So now if I recreate my boundary around a whole system, I can say that this is isolated, so that leaves the fact that it's a closed system and there's no heat transfer, so all the entropy change is due to entropy generated. So therefore, this entropy change of the system is 0.67, which also happens to be the entropy generated for the whole system itself.